Imagine this, a visitor from another star system tearing itself apart just millions of kilometres from the Sun. 3I-ATLAS, only the third confirmed interstellar object ever detected, has unleashed jets of gas and debris stretching 3 million kilometres, far beyond anything a normal comet could produce. And now a troubling question lingers. Did it simply break apart, scattering alien material across our solar system? Or is this a deliberate manoeuvre by something alien? Something we don't yet understand? Tonight, we dive into the mystery, the science, and the jaw-dropping possibilities. And even though scientists say there's no danger to Earth, by the end, you'll see the existential ripples this alien visitor could send our way. Stay tuned, because what happens next isn't just science, it's something no one prepared us for. If this mystery continues to have you hooked the way it has me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about this new development. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The Day the Sky Changed. On November 9th, 2025, a group of astronomers stacked a series of deep space photographs and saw something that shouldn't exist. Stretching from a single point in the darkness were two enormous jets of material. One reached roughly 1 million kilometres toward the Sun. The other extended 3 million kilometres in the opposite direction, away from our star into the void. The object at the centre of this display was called 3I-ATLAS, and it had just become the most confusing thing in our solar system. You need to understand something about scale here. 3 million kilometres is about 8 times the distance from Earth to the Moon. We're not talking about a little puff of gas. We're talking about structures so massive they dwarf planetary distances, erupting from what should be a relatively small chunk of ice and rock. When scientists first saw these images, the immediate question wasn't just what is this? It was what the hell happened. 3I-ATLAS is only the third confirmed interstellar object ever detected entering our solar system. Think about that for a moment. In all of human history, with all our telescopes and all our sky surveys, we've only confirmed 3 visitors from beyond our cosmic neighbourhood. The first was 1I/Oumuamua in 2017, that cigar-shaped mystery that sparked 1,000 debates. The second was 2I/Borisov in 2019, which at least behaved like a proper comet. And now we have this, discovered on July 1st, 2025, by the ATLAS survey operating in Chile. The trajectory told astronomers immediately that this wasn't one of ours. The orbit was hyperbolic, meaning it came from interstellar space, fell toward the Sun, and would eventually leave our system forever, never to return. It wasn't bound to our star like the comets and asteroids that were born here billions of years ago. This thing came from somewhere else entirely, carrying with it the chemical fingerprints of another stellar neighbourhood, another time, another formation process we can only guess at. Early estimates from Hubble Space Telescope images suggested the nucleus, the solid core of 3I-ATLAS, measured about 5.6 kilometres across. That's already enormous for a comet. For comparison, Halley's Comet, probably the most famous comet in human culture, has a nucleus roughly 11 kilometres long but much less massive overall. But here's where things get strange. Other data suggested 3I-ATLAS might actually be larger, perhaps significantly so. The numbers weren't adding up, and that was before anyone realised just how weird this object truly was. Under normal statistics, under the models we use to predict how many interstellar objects should pass through our system, something this large should be incredibly rare. We're talking about odds so low that detecting one in a human lifetime should be a surprise. And yet, here it was, big enough to see, bright enough to track, and behaving in ways that made seasoned astronomers start using phrases like unprecedented and inconsistent with known models. Then came the key turning point. 3I-ATLAS passed perihelion, its closest approach to the Sun, around October 29th, 2025. Perihelion is when comets typically brighten and become active, as solar heat vaporizes their ices and creates the familiar tail. But what happened to 3I-ATLAS wasn't familiar at all. Shortly after perihelion, observers started seeing those massive jets, that bizarre twin plume structure, and a cascade of changes that suggested something fundamental had shifted. So here's the core question, the one that's keeping scientists awake and filling preprint servers with speculative papers. What if 3I-ATLAS didn't just get bright and active near the Sun? What if it actually fragmented, broke apart under the stress of solar heating and tidal forces and internal gas pressure? What if we're looking at the wreckage of an interstellar visitor, shattered into pieces, spilling its alien guts across millions of kilometers of space? If that's true, if it really did break up, then we've just been handed an extraordinary gift. Fragmented material means increased surface area, which means more stuff exposed to our telescopes and spectrometers. We could be looking at the interior composition of an object formed around another star, potentially billions of years ago, processed by cosmic rays during eons of interstellar travel, now laid bare for us to study. It's like an alien autopsy, except the body is millions of kilometers wide and we're the detectives trying to piece together what killed it. But there's another possibility, one that's quieter in the official papers but louder in the hallways and the blog posts. What if it didn't fragment? What if 3I-ATLAS is still intact, and those jets, that energy, those impossible numbers, are being produced by something other than passive ice sublimation? What if we're looking at propulsion? What if we're looking at technology? That's not a mainstream conclusion yet. It's not even a widely accepted hypothesis, but it's on the table, and it's there because the data refuses to fit neatly into the box labelled normal comet. When your observations require either a radical rethinking of comet physics or a consideration of artificial origins, you're in uncharted territory. You're in the kind of territory where science meets philosophy, where discovery meets dread. We care about this because the implications branch in every direction. If 3I-ATLAS shredded, we gain unprecedented access to interstellar matter, we refine our models, we learn about how objects survive the journey between stars. If it didn't shred, if it's doing something else, then we might be looking at the first confirmed technological artifact from beyond our system. And if that's true, everything changes. So what happens next? What happens to us, to Earth, to our understanding of the cosmos, if this interstellar visitor really did break apart near the Sun? Or worse, what happens if it didn't? Part 2, when the numbers don't add up. Let's talk about what the telescopes actually saw, because the devil here is absolutely in the data. After perihelion, observers worldwide started capturing images of 3I-ATLAS that looked nothing like a standard comet. The twin jets were the headline, sure, but there was more. The tail structure kept changing. Amateur astronomers were posting images showing what looked like plumes, like the object was smoking, puffing out material in irregular bursts rather than the steady outgassing you'd expect from solar heating. Then there was the colour issue. Comets generally appear whitish or slightly yellowish, because they reflect sunlight and emit light from glowing gases. 3I-ATLAS turned bluer than the Sun itself at certain points. Not just a little blue, but measurably, significantly bluer. And the colour kept shifting, changing over days and weeks in ways that didn't correlate neatly with its distance from the Sun, or any predictable heating curve. It was like the object was cycling through different modes, different states, as if someone, or something, was flipping switches. Spectroscopy, the technique of splitting light into its component wavelengths to identify chemicals, revealed the next layer of strangeness. The James Webb Space Telescope and the Spherix mission both turned their instruments toward 3I-ATLAS and found a coma, the cloud of gas surrounding the nucleus, absolutely dominated by carbon dioxide. The ratio they measured was stunning. Carbon dioxide to water, roughly 8:1. For context, most solar system comets have ratios closer to 1:10 or even 1:100. Water ice is usually the main event. Here, carbon dioxide was the star, and water was barely a supporting actor. Why does that matter? Because it changes the entire energy budget. Carbon dioxide sublimates, turns from solid to gas, at different temperatures and rates than water ice. It also requires a specific amount of solar energy to drive that sublimation. When scientists calculated how much carbon dioxide 3I-ATLAS was spewing out, they ran into a problem. The surface area required to produce that much gas, given reasonable assumptions about solar heating and sublimation efficiency, was enormous. We're talking about an effective absorbing surface area exceeding 1,600 square kilometres, which corresponds to a spherical object roughly 23 kilometres in diameter. But the observed size, remember, was about 5.6 kilometres. The math didn't work. Either the object was much larger than Hubble images suggested, or the model was fundamentally broken, or something else was going on. The mass loss rate added another layer of confusion. Estimates suggested 3I-ATLAS was losing roughly 5 billion tonnes of material per month. Let that sink in for a second. 5 billion tonnes every month. The outflow velocity was pegged at about 0.4 kilometers per second, which is fast but not absurdly so for sublimating gas. Except the rate of mass loss wasn't steady. It was accelerating and accelerating steeply. Early in its approach, the object was losing maybe 150 kilograms per second. Within a few weeks, that figure skyrocketed to 2 million kilograms per second. That's an increase of over 10,000 times. To explain that kind of acceleration with standard comet physics, you need a distance to Sun power law of around negative 10.5. That's steep. Absurdly steep. Most comets follow power laws between negative 2 and negative 4. Negative 10.5 is off the charts. What does that steep power law mean? It means the object's activity was far more sensitive to solar distance than any normal comet should be. It means either the composition is wildly different, or the structure changed dramatically, or the physics isn't purely about solar heating anymore. It's the kind of number that makes scientists pause and double-check their calculations, because if it's real, it's pointing at something we don't fully understand. These anomalies cluster together into a picture that refuses to resolve cleanly. High carbon dioxide, insufficient surface area, extreme mass loss acceleration, colour changes, non-gravitational acceleration, which means the object's trajectory was being nudged by forces other than just the Sun's gravity, likely from a symmetric outgassing creating a rocket-like thrust. All of these could individually be explained by stretching existing comet models. But together, they form a pattern of weirdness that strains credibility. Fragmentation could explain some of this. If 3I-ATLAS broke into multiple pieces near perihelion, the total surface area would increase dramatically. More surface area means more sublimation, which means more gas, bigger jets, faster mass loss. Fragmentation could also explain the erratic behaviour, the changing tail structures, the appearance of plumes and bursts. Each fragment might be sublimating at slightly different rates, tumbling differently, contributing to a chaotic overall display. But fragmentation doesn't easily explain the colour shifts, or the extreme carbon dioxide dominance, or the precise timing of the activity surge. It's a good hypothesis, maybe the best natural hypothesis, but it's not a perfect fit, and that gap, that space between what fragmentation explains and what we observe, is where the more unsettling possibilities start to creep in. The data is real, the observations are solid. Multiple independent teams using different instruments are seeing the same anomalies. This isn't a case of bad calibration or a single rogue measurement. 3I-ATLAS is genuinely behaving in ways that push the boundaries of what we can model with known physics. We're at the edge, looking into a space where either our understanding of comets needs a major update, or we're seeing something that isn't a comet at all. So what do typical comets actually do, and how exactly does 3I-ATLAS break the mould? That's where we go next. Part 3, Comets versus Alien Visitors, the Expectation Gap. Let's establish the baseline, because before you can appreciate how strange 3I-ATLAS is, you need to understand what normal looks like. A standard comet is essentially a dirty snowball, a leftover chunk of ice and rock from the early solar system. As it approaches the Sun, solar radiation heats the surface, causing volatile materials, mostly water ice, to sublimate directly from solid to gas. This outgassing creates a hazy cloud called the coma, and the pressure of sunlight and solar wind pushes that gas and dust away from the Sun, forming the characteristic tail. It's a passive process, entirely driven by external energy. The comet doesn't do anything, it just sits there and melts. Typical solar system comets have compositions that reflect their birthplaces. They formed in the cold outer reaches of our planetary system, where water ice was abundant. You get water as the dominant volatile, with smaller amounts of carbon monoxide, carbon dioxide, methane, ammonia, and other simple molecules. When scientists measure the gas coming off these comets, the ratios are predictable. Water leads, everything else follows. The behaviour is also predictable. Brightness increases as the comet gets closer to the Sun, following smooth curves. Tails grow and shift based on the changing angle to the Sun and the solar wind. There might be occasional outbursts if a pocket of gas suddenly vents, but overall it's orderly. Now, look at 3I-ATLAS. Carbon dioxide dominates. The ratio is flipped. Instead of water leading the charge, you have carbon dioxide at 8 times the water abundance. That's not just unusual, that's a complete inversion of the normal pattern. It suggests this object formed in a very different environment, somewhere much colder or much richer in carbon dioxide ice than anything in our solar system. Or it suggests the surface has been chemically altered by some process we don't see here at home. Then there's the sheer scale of the jets. Most comets produce jets, sure, but they're relatively modest, extending maybe a few thousand to tens of thousands of kilometres. 3I-ATLAS is producing jets that stretch millions of kilometres. It's like comparing a garden hose to a fire hydrant. Actually, no. It's like comparing a garden hose to an industrial water cannon mounted on a dam. The volume and velocity of material being expelled is orders of magnitude higher than anything a typical comet can manage. The tail structures are also bizarre. Comets usually have 2 tails, a dust tail and an ion tail, and they point in roughly predictable directions based on solar wind and radiation pressure. 3I-ATLAS has shown multiple tails, changing configurations, structures that appear and disappear, and an overall morphology that shifts day to day. It's as if the object can't decide what kind of tail it wants, or as if multiple processes are fighting for control. Here's the nucleus size problem again, because it's central to understanding the gap. If you want to sublimate enough carbon dioxide to produce the observed jets and coma, you need a certain amount of surface area exposed to sunlight. The calculations are straightforward. You take the solar flux at the comet's distance, multiply by the surface area, factor in how efficiently carbon dioxide absorbs that energy and sublimates, and you get an expected mass loss rate. When scientists did this math for 3I-ATLAS, the required surface area implied an object far larger than what Hubble images showed. Fragmentation offers a way out of that paradox. If the nucleus broke into many smaller pieces, each piece has its own surface area. Add them all up, and you could get the necessary total area without needing a single giant nucleus. It's like shattering a boulder into gravel. The total mass is the same, but the total surface area is much higher, because all those little pieces have their own exteriors. More surface equals more sublimation equals bigger jets. The hypothesis fits. But does it fit perfectly? Not quite. Fragmentation should produce observable signatures. You should see distinct multiple nuclei, separate sources for the jets. Observers have been looking, and while the data is messy and the object is far away, there's no clear consensus yet on whether we're seeing one nucleus or 16. Some analyses suggest multiple sources, others suggest a single active core with asymmetric outgassing. The ambiguity is frustrating. There's also the alternative, the one that doesn't rely on natural breakup. What if 3I-ATLAS isn't behaving like a normal comet because it isn't a normal comet? What if those jets are exhaust? What if the colour shifts are thermal signatures from active systems? What if the non-gravitational acceleration is deliberate course correction? That's speculation. Absolutely. But it's speculation driven by the data's refusal to fit neatly into any natural box. To use an analogy, imagine you find a bird flying over your house. You expect it to flap its wings, glide, maybe soar on thermals. Now imagine this bird is glowing blue, shooting fire from its tail, and moving at 300 kilometers per hour in a straight line with no visible means of propulsion. At some point, you stop trying to explain it as a weird bird and start considering that maybe it's not a bird at all. Maybe it's a drone. Maybe it's something built. 3I-ATLAS is our glowing blue bird. The expectation was a comet. The observation is something that stretches the definition of comet to the breaking point. Either it's a comet doing things we've never seen a comet do, in which case our models need serious revision, or it's something else, in which case our models are fine, but our assumptions about what's out there just got shattered. So where does that leave us? We have 2 major scenarios on the table. Scenario A is the natural breakup, the violent fragmentation hypothesis. Scenario B is the surviving visitor, the possibility that this object remains intact and is doing something that looks less like physics and more like engineering. Let's explore what each scenario actually means, starting with the breakup. Part 4. Scenario A. The violent breakup. Imagine you're a 5-kilometre ball of ice and rock that's spent millions of years drifting through the galaxy. You've been irradiated by cosmic rays, bombarded by micrometeoroids, and chilled to near absolute zero for longer than human civilization has existed. Now, you're falling toward a star, and that star is pumping energy into you at a rate you've never experienced. Your surface starts to heat, your ices begin to sublimate, Gas builds up under your crust, the pressure increases, the tidal forces from the star's gravity start pulling harder on your near side than your far side. Something has to give. That's the natural fragmentation hypothesis in a nutshell. Under extreme conditions near perihelion, 3I-ATLAS could have simply cracked apart. The stress of solar heating, the internal gas pressure from rapidly sublimating volatiles, and the tidal gradient from the sun's gravity could combine to exceed the object's structural strength. Comets aren't solid monoliths, they're rubble piles, loosely bound collections of smaller chunks held together by weak gravity, and maybe some ice acting as glue. Hit them with enough stress, and they come apart. We have precedent for this. The most famous example is Comet Shoemaker-Levy 9, which broke into at least 21 distinct fragments after passing too close to Jupiter in 1992. Those fragments then famously collided with Jupiter in 1994, creating spectacular impact scars visible even in small telescopes. Jupiter's tidal forces ripped Shoemaker-Levy 9 apart, and while 3I-ATLAS isn't dealing with Jupiter's gravity, it is dealing with intense solar heating and a close perihelion passage that could produce similar effects. If 3I-ATLAS broke up, the fragments would spread out along the object's orbit, creating a long trail of debris. The pieces would separate over time, moving at slightly different speeds due to their different masses and the varying rocket effects from their individual outgassing. You'd end up with something like a string of pearls, dozens or hundreds of kilometers long initially, eventually stretching to millions of kilometers as the fragments diverge. Each fragment would have its own surface area exposed to sunlight. This is key. Breakup dramatically increases the total surface area for a given mass. Think of it like crushing an ice cube versus leaving it whole. The crushed ice melts faster because more of it is exposed to warm air. Same principle here. More surface area means more sublimation, which means more gas production, which means bigger, brighter jets and a more active coma. The observed surge in activity after perihelion fits perfectly with a fragmentation event that suddenly multiplied the effective surface. Avi Loeb, the Harvard astrophysicist who's become a prominent voice in the discussion around interstellar objects, suggested in one of his blog posts that 3I-ATLAS might have fractured into at least 16 pieces. That number comes from trying to reconcile the observed activity levels with the required surface area. If you need 16 times more surface area than a 5.6 kilometre sphere provides, then you need roughly 16 fragments of comparable size, or many more smaller ones. The math is approximate, but it gives you a sense of scale. We're not talking about a little crack, we're talking about wholesale disintegration. What would that mean for Earth and the inner solar system? The good news first, there's no collision threat. 3I-ATLAS is on a hyperbolic trajectory that doesn't intersect Earth's orbit. The object came from interstellar space, swung around the sun, and is heading back out into the galaxy. Even if it broke into 1,000 pieces, those pieces are all following roughly the same path, and that path doesn't come near us. The closest approach to Earth is on December 19th, 2025, but even that is millions of kilometers away, far beyond any danger zone. The less good news, though it's still not threatening, is that fragmentation does produce a lot of dust and small debris. That material spreads out, gets pushed around by solar wind and radiation pressure, and forms a diffuse cloud along the orbit. If Earth happened to pass through a dense part of that cloud, we might see some weak meteor activity, like a very faint meteor shower with particles burning up harmlessly in the upper atmosphere. Space-based instruments, satellites and telescopes might experience slightly increased dust impacts, but we're talking about microscopic particles at most. It's an annoyance, not a disaster. There could also be interactions with the solar wind. Charged dust particles can affect the local plasma environment, creating small perturbations in the magnetic fields and particle flows near the sun. Scientists studying solar physics and space weather might notice blips in their data, but again, nothing that threatens Earth directly. Observationally, if 3I-ATLAS did break up, we should be able to see evidence over the coming weeks and months. The tail morphology should continue to evolve as fragments separate and create distinct plumes. High-resolution imaging might resolve multiple nuclei, distinct bright spots where individual fragments are most active. The overall brightness might gradually decline as the fragments move away from the sun and their activity drops. Dust trails should become more elongated and diffuse. The timeline is important. The closest Earth approach on December the 19th gives astronomers a golden opportunity. The object will be relatively nearby, cosmically speaking, which means better angular resolution and more detailed images. If there are fragments, if there are multiple pieces, that's when we're most likely to see them clearly. Telescopes around the world are already gearing up for that date, scheduling observation time, preparing instruments. It's like waiting for a jury to deliver a verdict. Scenario A, the violent breakup, is the safest interpretation scientifically. It requires no new physics, no exotic explanations. It's just a comet under stress doing what comets sometimes do. It's parsimonious, as scientists like to say, meaning it explains the observations with the fewest assumptions. But parsimony doesn't guarantee truth. Sometimes the simplest explanation is still wrong. Sometimes reality is weirder than the safe bet. So what if 3I-ATLAS didn't break up? What if it's still intact, and all that activity, all those jets, all that impossible energy is coming from something else? That's scenario B, and that's where things get unsettling. Part 5, Scenario B, the surviving visitor. Let's consider the alternative, the scenario that makes scientists uncomfortable but can't be dismissed entirely. What if 3I-ATLAS did not fragment? What if the nucleus is still intact, holding together despite the hellish conditions near the Sun, and the jets, the colour shifts, the non-gravitational acceleration are all being produced by something other than passive sublimation? What if we're looking at propulsion? The clues are already there in the data. Non-gravitational acceleration means the object's trajectory is being altered by forces other than gravity. For a comet, that's usually explained by the rocket effect. Gas sublimating from the surface shoots off in one direction, pushing the nucleus in the opposite direction, like a tiny thruster. That's normal. But the magnitude and pattern of 3I-ATLAS's acceleration don't fit the typical profile. The nudges are too strong, too coordinated, as if something is steering. Then there's the colour shift. The object turned bluer than the Sun, meaning it was emitting or reflecting light at shorter wavelengths, higher energies. Typical comet activity doesn't do that. Sublimation produces visible and ultraviolet light from excited gas molecules, but not in a way that systematically shifts the overall colour bluer than the solar spectrum. You'd need either a very unusual chemical composition or an additional energy source, something heating or exciting the material beyond what sunlight alone can do. The energy budget problem is the big one. To produce jets as powerful as those observed, you need an exhaust velocity much higher than the thermal speeds of sublimating gas. Sublimation gives you velocities on the order of a few hundred meters per second at most. The jets from 3I-ATLAS are clocked at 400 meters per second, which is already at the high end. But to explain the observed thrust, the non-gravitational acceleration, you'd ideally want exhaust velocities in the range of 3 to 50 kilometers per second. That's not sublimation anymore. That's propulsion territory. That's ion thrusters, chemical rockets, something actively accelerating material. A.V. Loeb, in one of his Medium blog posts, put it bluntly. Houston, we have a problem. The implication is clear. If 3I-ATLAS is intact, if the jets are coming from a single body rather than multiple fragments, then the energy required exceeds what solar heating can provide through standard comet processes. You need another source. You need engines. What would a surviving, actively propelled interstellar craft look like? Imagine a probe, a vessel designed to travel between stars, equipped with systems to adjust its trajectory, deploy smaller units, study environments it passes through. As it approaches a star, it might activate propulsion to correct its course, using stored energy or harvesting solar radiation. The jets we see could be exhaust plumes from those systems, directed bursts of ionized gas or plasma. The colour shifts could be thermal signatures from the engine cycling on and off. The changing tail morphology could be the result of different thrusters firing at different times, creating a complex evolving structure. This is speculation, absolutely. There's no smoking gun here, no radio signal, no clear artifact, no definitive proof. But the possibility exists in the space between what we observe and what natural physics comfortably explains. If 3I-ATLAS is artificial, if it's technology, then we're not just studying a comet. We're studying someone else's engineering, someone else's design, someone else's decision to send something into our system. What would you watch for if you suspected artificial origins? First, an intact nucleus. If high-resolution imaging shows a single, coherent body rather than multiple fragments, that rules out the natural breakup scenario and forces you to explain the activity some other way. Second, coordinated jets, if the plumes are firing in patterns, if they're directional and timed, that suggests control rather than random outgassing. Third, subtle maneuvers. If the trajectory shows small, deliberate changes that don't match sublimation-induced rocket effects, that's a red flag. You'd also look for repeated patterns. Does the object brighten and dim in regular cycles? Does the colour shift repeat? Does the activity surge correspond to specific distances or alignments? Natural processes can produce periodicities, like a rotating nucleus exposing different areas to sunlight, but artificial systems might have different signatures, different rhythms. You'd want to rule out everything natural before claiming anything artificial, but you'd keep your instruments ready, your data pipelines open, just in case. Then there's the question of communication. If this were a probe, would it be transmitting? Would it be listening? Efforts to search for signals from 3I-ATLAS have so far turned up nothing. But the absence of evidence isn't evidence of absence. Maybe it's dormant. Maybe it uses frequencies or modulations we're not monitoring. Maybe it's designed to be silent. Or maybe it's just a rock, and we're seeing patterns in noise because our brains are wired to find agency and intention where none exists. The philosophical stakes here are enormous. If 3I-ATLAS is technology, if it's artificial, then we're not alone, and we've just had our first confirmed contact with something built by someone else. That changes everything. It changes how we see ourselves, our place in the galaxy, our future. It raises questions about intention. Why is it here? Is it observing us? Is it passing through by chance or by design? And if it's designed, what does that say about whoever designed it? Even entertaining this possibility feels dangerous, like crossing a line between science and science fiction. But science has crossed that line before and found reality on the other side. When quasars were discovered, some scientists briefly considered the possibility they were artificial, beacons built by advanced civilizations. They weren't, but the question was worth asking. When pulsars were discovered, the regular radio pulses were so precise that astronomers jokingly called the first one LGM-1, for little green men. It turned out to be a neutron star, a natural explanation, but the speculation was legitimate given the data. 3I-ATLAS might be the same. A weird comet, nothing more. But the data is strange enough, the anomalies stacked high enough, that the artificial hypothesis can't be dismissed out of hand. Not yet. Not until we have better images, better spectra, better trajectories. Not until December 19th, when the object makes its closest approach and we get our best look. So here's where we stand. Scenario A says fragmentation, natural processes, a comet doing comet things under extreme conditions. Scenario B says intact, artificial, something that looks less like physics and more like engineering. Both are on the table. Both have supporting evidence. Both have gaps and problems. And the truth, whatever it is, will reshape how we think about interstellar visitors, about the galaxy, about whether we're alone. But 3I-ATLAS isn't the only strange thing happening in the cosmos right now. There are other stories, other discoveries, other challenges to our assumptions, and they all connect to this central theme. The universe is weirder than we thought, and we're just beginning to realize how much we don't know. That's where we go next, into the depths of composition, the mysteries of origin, and the broader implications of living in a galaxy that refuses to follow our rules. Part 6. Alien Ice, Galactic Rays and Origin Mysteries. Now we drill down into the chemistry, because the composition of 3I-ATLAS is just as strange as its behaviour, maybe stranger. When the James Webb Space Telescope pointed its infrared instruments at the comet's coma, the spectra that came back were unlike anything from a typical solar system comet. The carbon dioxide to water ratio, as mentioned, was roughly 8:1. That's extreme, but the deeper you look, the weirder it gets. Spherex, another space-based observatory, confirmed the findings and added more detail. The coma was bright in carbon dioxide emission, glowing intensely in the infrared wavelengths where carbon dioxide molecules radiate after being excited by sunlight. Water and carbon monoxide, the other common volatiles, were barely detectable. The production rates for water and carbon monoxide were orders of magnitude lower than the carbon dioxide rate. It's as if this object is made of dry ice with just a trace of frost. Polarimetry, a technique that measures how light is polarized after reflecting off or scattering through a material, added another layer. 3I-ATLAS showed a deep negative polarization branch, hitting minus 2.7% at a phase angle of 7 degrees. For non-experts, that's a measure of how much the reflected light's electric field is aligned in a particular direction. Negative polarization branches are rare and usually indicate very specific grain sizes and compositions in the dust and gas. The value measured for 3I-ATLAS is unprecedented among comets and asteroids. It doesn't match anything in our catalogue. So what does all this mean? The high carbon dioxide abundance suggests 3I-ATLAS formed in a region of its parent protoplanetary disk, where carbon dioxide ice was more stable than water ice. In our solar system, that corresponds to the outer regions beyond Neptune, where temperatures drop low enough that carbon dioxide doesn't sublimate away, but water ice is still more abundant. For carbon dioxide to dominate, you'd need an even colder environment, or one with a different initial chemical mix, enriched in carbon and oxygen but depleted in hydrogen. That points to a formation region far from the star, or around a star with a different composition than our Sun. There's also the cosmic ray hypothesis. Over millions of years of interstellar travel, an object like 3I-ATLAS would be continuously bombarded by galactic cosmic rays, high-energy particles that permeate the galaxy. These particles can penetrate several meters into ice and rock, breaking chemical bonds, creating new molecules, altering the surface composition. One proposed mechanism is that cosmic rays convert carbon monoxide, which is common in interstellar ice, into carbon dioxide through radiolysis, a radiation-driven chemical reaction. Over time, the outer layers of the object would become enriched in carbon dioxide, creating an organic rich crust that differs chemically from the interior. This cosmic ray processing hypothesis is attractive because it explains not just the high carbon dioxide, but also the unusual polarization. The crust would be made of complex organic molecules, carbon-rich grains, materials that scatter light differently than clean ice or silicate dust. When those grains are ejected as part of the coma, they produce the polarization signature we observe. It's a self-consistent story, one that ties the composition to the object's long journey through interstellar space. But it also raises questions. If 3I-ATLAS spent millions or even billions of years between stars, where did it come from originally? Every interstellar object has an origin, a star system where it formed, a planetary disk where it condensed out of gas and dust. Based on the trajectory, astronomers can work backwards and estimate the direction 3I-ATLAS came from in the galaxy. The results suggest it didn't come from any nearby star system. It came from the general direction of the galactic centre, or perhaps from a region of active star formation hundreds of light-years away. Pinpointing a specific source is nearly impossible, but the implication is that this object has been wandering for a very long time, perhaps since the early epochs of our galaxy, when star formation was more vigorous and planetary systems were less settled. The composition also tells us something about the diversity of planetary systems out there. If 3I-ATLAS formed around another star, its chemistry reflects the conditions in that system. The carbon dioxide dominance suggests a colder, carbon-rich disk, maybe one that formed from a molecular cloud with higher metallicity or different isotopic ratios. It's a glimpse into alien geology, alien mineralogy, alien ice physics. Every measurement we make is a data point about how planets and comets form elsewhere, expanding our sample size beyond the single example we have in our own solar system. There's also the population question. If 3I-ATLAS is representative of a class of interstellar objects, radiation-processed bodies with organic-rich crusts and high carbon dioxide content, then there could be many more like it passing through the solar system undetected. Most would be too faint or too far away to spot, especially if they don't brighten significantly as they approach the Sun. Our current detection methods are biased toward large, active objects. We're missing the small, dark, inactive ones. 3I-ATLAS might be the tip of an iceberg, the one bright example in a population of thousands or millions that remain invisible. That has implications for how we think about interstellar material exchange in the galaxy. Stars don't exist in isolation. They're born in clusters. They migrate through the galactic disk. They gravitationally perturb each other's comet clouds. Over billions of years, objects get ejected from one system and captured by another, or they simply drift through interstellar space, carrying with them the chemical fingerprints of their origins. The galaxy is constantly shuffling its deck, mixing materials, exchanging building blocks. 3I-ATLAS is part of that process, a messenger from somewhere else, carrying information encoded in its atoms. The alien composition also tilts the puzzle toward the more exotic interpretations. If this object is so chemically different from anything in our solar system, if its crust has been processed by cosmic rays into organic materials we don't fully understand, then maybe its behaviour near the Sun is equally alien. Maybe the physics governing how it sublimates, how it releases gas, how it responds to solar heating, is different from what we're used to. Maybe we're applying models built for solar system comets to something that doesn't play by those rules. Or, and this is where the speculation gets uncomfortable again, maybe the composition is deliberate. If you were building an interstellar probe, you'd want materials that could survive the harsh environment of space for long durations. You'd want a crust that could shield against cosmic rays, that could self-repair or at least remain stable under radiation. You'd want volatiles that could be used as propellant, stored in stable ices that sublimate predictably near a star. Carbon dioxide fits that bill. It's dense, it sublimates cleanly, it's easy to handle chemically. A carbon dioxide-rich composition might not be natural. It might be engineered. That's a stretch. Absolutely. There's no evidence that the composition is artificial. But once you start seeing anomalies in one area, the behaviour, it becomes harder to ignore anomalies in another area, the chemistry. They reinforce each other, building a case that something about 3I-ATLAS is fundamentally different from expectation. The cosmic ray processing idea is the best natural explanation for the composition, and it's a good one. It fits the data, it's supported by physics, it's testable. If we could sample the surface directly, if we could analyse the organic crust in a lab, we could confirm or refute it. But we can't. We're stuck observing from millions of kilometres away, inferring chemistry from photons, building models from spectra. It's detective work with incomplete clues, and the jury is still out. What's clear is that 3I-ATLAS is chemically alien. Whether that alienness is the result of natural processes in a different stellar environment, or radiation exposure over eons, or something more deliberate, we don't yet know. But the composition matters, because it shapes how the object behaves, how it responds to the Sun, and ultimately whether it breaks apart or survives intact. So we've established that 3I-ATLAS is chemically weird and behaviourally anomalous. The next question is physical. If it did break apart, how exactly would that happen, and what would the debris field look like? That's where we turn now, into the mechanics of fragmentation and the potential aftermath. Part 7. Fracture, dust and debris. Fields, what could come next? Breaking apart sounds simple, but the mechanics are anything but. A comet isn't a solid rock. It's a rubble pile, a loosely bound collection of smaller chunks, pebbles, boulders, all glued together by ice and held by weak mutual gravity. The tensile strength, the force required to pull it apart, is low. You don't need much stress to overcome the cohesion, but you do need the right kind of stress in the right places at the right time. Solar heating is the first culprit. As 3I-ATLAS fell toward the Sun, the surface temperature skyrocketed. Ice on the day side began sublimating rapidly, turning directly from solid to gas. But that process isn't uniform. Some areas might be darker, absorbing more heat. Others might be covered in dust that insulates the ice beneath. The result is differential heating, hot spots and cold spots, thermal gradients that create internal stress. Ice expands and contracts with temperature changes, and if those changes are rapid and uneven, cracks form. Then there's internal gas pressure. As volatiles sublimate beneath the surface, gas gets trapped under layers of dust and less volatile ice. Pressure builds, eventually something gives. The crust ruptures, gas explodes outward, carrying dust and fragments with it. This is what causes the dramatic outbursts sometimes seen in comets. Sudden brightenings where a pocket of gas vents all at once. If enough gas builds up, if the structure is weak enough, the whole nucleus can shatter. Tidal forces add another layer. The Sun's gravity pulls harder on the near side of the comet than the far side, creating a stretching effect. For a large object passing close to a massive body, this tidal gradient can be immense. That's what tore Shoemaker-Levy 9 apart near Jupiter. 3I-ATLAS passed perihelion at a distance of about 1.35 astronomical units, roughly 135 million kilometres from the Sun. That's farther than Earth, so the tidal forces aren't as extreme as they would be closer in. But combined with the internal stresses from heating and gas pressure, tidal forces could still contribute to fragmentation. Rotation also matters. If the nucleus is spinning, centrifugal force pushes outward, adding to the stress. Comets can spin quite fast, sometimes with periods of just a few hours. If 3I-ATLAS was already rotating and then began outgassing asymmetrically, the jets could act like tiny rocket engines, spinning the nucleus faster or changing its rotation axis. That adds more mechanical stress, more potential for breakup. If fragmentation occurred, the pieces would initially stay close together, maybe just a few kilometers apart, but they'd be moving at slightly different velocities due to their different masses and the varying thrust from their individual outgassing. Over hours and days, the fragments would spread out along the orbit, creating a linear structure. Over weeks and months, that structure would stretch to millions of kilometers, a string of icy pearls slowly diverging. Avi Loeb's estimate of at least 16 fragments comes from matching the observed activity level to the required surface area. If the original nucleus was 5.6 kilometers across, its surface area was roughly 98 square kilometers. To get 16 times more area, you'd need either 16 similarly sized pieces or many more smaller ones. The exact number depends on how the breakup happened, whether it was a clean split into large chunks or a chaotic shattering into a cloud of debris. Each fragment would behave like a mini comet. It would have its own coma, its own jets, its own outgassing pattern. From a distance, the combined glow of all those fragments might look like a single extended source, a fuzzy blob rather than distinct points. That could explain why observers haven't definitively resolved multiple nuclei yet. The fragments might be too close together, or too faint individually, or lost in the overwhelming brightness of the combined coma. The debris field would also include dust, lots of it. Fragmentation exposes fresh surfaces, which sublimate more aggressively, which ejects more dust. That dust spreads out under radiation pressure from sunlight, forming a broad cloud along the orbit. The particles range in size from submicron grains to millimeter-sized pebbles. The smallest ones are pushed away from the sun most strongly, creating a fan-shaped distribution. The larger ones follow paths closer to the original orbit. What does that mean for us? Earth's orbit is nowhere near 3I-ATLAS's trajectory, so we won't pass through the debris field. But other spacecraft might. Satellites in high orbits, interplanetary probes, observatories monitoring the sun, they could potentially encounter stray dust particles. The risk is minimal, but it's not zero. A single grain hitting a sensitive instrument at interplanetary speeds can cause damage. Mission planners are aware of this, and they're tracking the comet's trajectory and predicted debris distribution just in case. There's also the solar wind interaction. Dust particles in space pick up electric charge from ultraviolet light and collisions with plasma. Charged dust can interact with the solar wind, the stream of charged particles flowing out from the sun. In dense dust clouds, this interaction can create local disturbances in the magnetic field, measurable by instruments on spacecraft. Scientists studying space weather might see anomalies in their data, little blips that correspond to the comet's passage. Visually, from Earth, the debris field might not look like much. The comet is already faint, requiring decent telescopes to see. If it breaks into many pieces, each piece might be even fainter, harder to track. But the combined glow could create interesting effects, like a stretched-out tail or multiple tail structures. Amateur astronomers with backyard telescopes have been monitoring 3I-ATLAS, and some have reported seeing changes in the tail morphology, hints of complexity that could be fragments. The timeline for observation is critical. December 19th, 2025 is when 3I-ATLAS makes its closest approach to Earth, about 0.6 astronomical units away, roughly 90 million kilometers. That's the best opportunity we'll have for high-resolution imaging, for spectroscopy, for detailed characterization. If fragments exist, that's when we'll see them most clearly. If the nucleus is intact, that's when we'll measure its size and shape most accurately. Telescopes worldwide are coordinating observation campaigns, scheduling time, preparing instruments. It's a brief window, just a few days when the geometry is optimal, and then the comet continues outward, fading into the distance. What if the fragmentation hypothesis is wrong? What if observations on December 19th show a single, intact nucleus with no sign of breakup? Then we're back to scenario B, back to the unsettling possibility that the activity, the jets, the energy, are coming from something other than natural sublimation. That brings us back to the artificial hypothesis, the speculation that refuses to go away. But before we fully embrace that speculation, we need to address the controversies, the politics, the battles over data access and scientific credibility. Because this story isn't just about a comet or a probe or whatever 3I-ATLAS turns out to be, it's also about how science operates under pressure, how transparency shapes narratives, and how extraordinary claims require extraordinary evidence. That's next. Part 8. Probe or protein? Technology, speculation and big questions. Let's say it out loud. The artificial hypothesis. The idea that 3I-ATLAS might be technology, a probe, an artifact, something built by someone else. It's the elephant in the room, the possibility that lurks beneath every anomaly, every unexplained data point. And while mainstream astronomers are careful, cautious, reluctant to speculate without hard evidence, the speculation is happening anyway, in blogs, in preprints, in conversations at conferences, and in the public imagination. Avi Loeb has been the most prominent voice suggesting we shouldn't rule out artificial origins. He's no fringe figure. He's a tenured professor at Harvard, former chair of the astronomy department, a respected theorist with hundreds of papers to his name. He's also willing to ask uncomfortable questions, to push against the scientific consensus when the data warrants it. His involvement with Oumuamua, where he suggested it might be a light sail, made him a controversial figure. Some colleagues praised his willingness to think outside the box. Others criticised him for going too far, for speculation that they felt crossed into sensationalism. With 3I-ATLAS, Loeb is asking similar questions. In his Medium posts, he's laid out the evidence list. The carbon dioxide dominance that doesn't fit comet models. The energy budget problem where the required surface area exceeds the observed size. The non-gravitational acceleration that suggests thrust rather than passive outgassing. The colour shifts that hint at additional energy sources. The statistical oddity of an object this large arriving from interstellar space. Each piece individually might have a natural explanation, but together they form a pattern that resists easy categorization. He's also pointed out the trajectory characteristics. 3I-ATLAS came in on a retrograde orbit, moving opposite to the general direction of solar system bodies. That's not impossible for a natural interstellar object, but it's less common. The orbit is also roughly aligned with the ecliptic plane, the flat disk where most planets orbit. Again, not impossible, but statistically less likely for a random interloper from the galaxy. If you were designing a probe to study a solar system, you might choose a trajectory that passes through the ecliptic where most of the interesting stuff is. Then there's the engine behaviour language Loeb uses. He suggested that jets with exhaust velocities in the 3 to 50 km per second range look less like sublimation and more like propulsion. Ion thrusters, used on spacecraft like Dawn and Deep Space One, produce exhaust speeds in that range by accelerating ions with electric fields. Chemical rockets can do even better. If 3I-ATLAS has jets operating at those velocities, and if the nucleus is intact rather than fragmented, then you need an explanation for where the energy is coming from. Solar heating alone doesn't cut it. The phrase Houston, "we have a problem," isn't just dramatic. It's Loeb's way of saying that the conventional models are insufficient, that something doesn't add up, and that we need to seriously consider alternatives. Those alternatives include exotic natural processes, sure, but they also include the possibility of technology. What would constitute strong proof? That's the key question. Speculation is easy. Proof is hard. If you wanted to definitively show that 3I-ATLAS is artificial, what would you look for? A radio signal would be the smoking gun, a deliberate transmission in a narrow frequency band that can't be explained by natural emissions. Scientists have searched for signals from 3I-ATLAS using radio telescopes. So far, nothing. But absence of evidence isn't evidence of absence. Maybe it's not transmitting. Maybe it's using a frequency or modulation we're not monitoring. Optical signals would be another clue. Deliberate flashes, pulses, patterns in brightness that don't correlate with rotation or outgassing. So far, the brightness changes seem consistent with a rotating, asymmetrically active nucleus. But subtle patterns might be buried in the noise, waiting for more careful analysis. Trajectory maneuvers would be compelling. If the object made a course correction, a deliberate change in velocity that can't be explained by gravitational interactions or outgassing, that would be very hard to explain naturally. Monitoring the orbit over months and years will be critical. Small deviations from the predicted path could be significant. Then there's the question of intent. If this is a probe, why is it here? Is it observing our solar system? Is it passing through by chance? A derelict left over from some ancient mission, now drifting aimlessly? Is it actively studying us, collecting data, reporting back? Or is it something else entirely, a piece of interstellar infrastructure, a navigation beacon, a warning buoy? The possibilities multiply once you admit the hypothesis. The public fascination is undeniable. Celebrities have weighed in. Kim Kardashian posted about 3I-ATLAS on social media, asking if it's aliens. Joe Rogan discussed it on his podcast, inviting speculation from his massive audience. Coverage has appeared in outlets ranging from People magazine to the New York Post to more serious science publications. The hype is real, and it's cutting both ways. On one hand, public interest drives funding, encourages observation campaigns, brings attention to astronomy. On the other hand, it creates pressure for sensational conclusions, rewards speculation over rigour, and can poison the well of scientific discourse. Scientists are caught in the middle. They need to maintain credibility, which means being careful, conservative, not making claims they can't back up. But they also need to be honest about uncertainty, about the fact that 3I-ATLAS doesn't fit neatly into existing categories. Saying we don't know is scientifically accurate, but it's not satisfying, and it leaves room for others to fill the void with wilder ideas. The risk of speculating too freely is that you lose credibility if you're wrong. Loeb has experienced this. His Oumuamua light sail hypothesis drew criticism, and while some of that criticism was legitimate scientific disagreement, some of it was personal, attacking his motives or competence. He's developed a thick skin, but the dynamic is toxic. Science works best when people can propose ideas without fear of career damage, but it also needs mechanisms to filter out nonsense, to distinguish speculation from evidence-backed claims. The reward, though, if the artificial hypothesis turned out to be true, would be incalculable. Confirmation of extraterrestrial technology, even a derelict probe, would be the most significant discovery in human history. It would prove we're not alone, that intelligence has arisen elsewhere, that civilizations exist or have existed beyond Earth. It would reshape philosophy, religion, culture, politics. It would give us a benchmark, a comparison point, a glimpse into what's possible. It would be the beginning of a new era, but we're not there yet. We're in the messy middle, where the data is ambiguous, the interpretations contested, and the truth unknowable until we get better observations. December 19th is coming. The telescopes are ready. The questions are sharpening. And whatever we learn, whether 3I-ATLAS is a broken comet or something stranger, the answers will matter. For now, the technology speculation remains just that, speculation. But it's informed speculation, driven by real anomalies, real data that challenges our models, and that's worth paying attention to, even if it makes us uncomfortable. The next part of this story isn't about the object itself. It's about the process, the politics, the battles over who gets access to data, and how transparent the scientific community should be when dealing with extraordinary claims. That's where we go next. Part 9. Who gets the picture? Politics, data, and the great scientific trust. Science likes to present itself as objective, transparent, driven purely by evidence and reason, and at its best, it is. But science is also done by humans, funded by institutions, subject to politics and egos and competition. When something as strange as 3I-ATLAS appears, those human factors come to the forefront, and the battle over data access becomes almost as interesting as the object itself. Here's the situation. Multiple observatories have been studying 3I-ATLAS since its discovery. Ground-based telescopes in Chile, Hawaii, Arizona, and elsewhere have been tracking it, taking images, measuring brightness and spectra. Space-based instruments like Hubble, James Webb, and SphereX have contributed infrared and ultraviolet data. Amateur astronomers worldwide have added their own observations, filling in gaps and providing continuous coverage that professional telescopes can't match. But not all of this data is publicly available. Some is proprietary, held by research teams with exclusive access for a limited time to analyse and publish their findings. That's standard practice in astronomy. Observing time is precious, competitively awarded, and the teams that win that time get first crack at the data. The idea is to reward the effort and expertise that goes into making the observations, to give researchers time to do careful analysis before releasing raw data that others might misinterpret or scoop. The problem arises when the object in question is so unusual, so potentially significant, that the public interest exceeds the normal scientific process. People want answers now. They want to see the images, read the spectra, evaluate the evidence themselves, and when data is held back, even for legitimate reasons, suspicion grows. Is something being hidden? Are scientists covering up evidence? Is there a conspiracy to suppress the truth about alien visitors? That suspicion reached a peak when a US lawmaker, responding to constituent pressure and public fascination, formally requested that NASA release high-resolution images of 3I-ATLAS, taken by the HiRISE camera on the Mars Reconnaissance Orbiter. Wait, you might say, HiRISE is designed to photograph Mars, not comets. True, but the camera has exceptional resolution, and if pointed at 3I-ATLAS during a favourable alignment, it could potentially resolve surface features or multiple nuclei that other instruments can't. The request was denied, officially because HiRISE wasn't tasked for that observation, and reallocating resources would disrupt planned Mars science. But the denial fueled speculation that NASA has images showing something extraordinary and is withholding them. There's no credible evidence for that conspiracy. HiRISE almost certainly hasn't imaged 3I-ATLAS, and even if it had, the distance and geometry would make resolving fine details nearly impossible. But the incident illustrates the tension between scientific process and public demand for transparency. When you're dealing with something that could potentially be the first confirmed extraterrestrial technology, the usual rules feel inadequate. Peer review is another flashpoint. Many of the findings about 3I-ATLAS have appeared in preprints, papers posted on servers like Arxiv before formal peer review and journal publication. Loeb's medium blog posts are even less formal, more akin to public commentary than scientific publication. That's not inherently bad. Preprints allow rapid dissemination of results, and blog posts can communicate ideas to a broader audience. But they also bypass the quality control that peer review provides. Mistakes can propagate, speculation can be presented as fact, and readers without expertise might struggle to distinguish credible analysis from fringe theories. The challenge is that peer review takes time, often months or even years. For a fast-moving object like 3I-ATLAS, waiting for formal publication means lagging behind the observations. By the time a peer-reviewed paper appears, the comet might have moved beyond useful observation range, or new data might have rendered the analysis obsolete. So researchers are caught between the need for speed and the need for rigour. Public trust in science is also at stake. The broader population is watching, reading headlines, forming opinions. If scientists seem evasive, if they withhold data, or speak in jargon-heavy language that obscures more than it clarifies, trust erodes. Conspiracy theories flourish in environments where information is scarce or contradictory, and once trust is lost, it's hard to rebuild. Celebrity involvement complicates things further. When Kim Kardashian tweets about 3I-ATLAS to her hundreds of millions of followers, when Joe Rogan devotes podcast segments to speculating about alien probes, the narrative escapes scientific control. These figures have reach and influence far beyond what any astronomer can command. Their commentary, even if well-intentioned, can amplify misinformation, create unrealistic expectations, or trivialize serious questions. At the same time, celebrity attention brings eyes and minds to the topic. It raises public awareness of astronomy, of the search for extraterrestrial intelligence, of the mysteries still unsolved in our universe. It can inspire young people to pursue science, to ask big questions, to look up at the sky with wonder. The trick is balancing enthusiasm with accuracy, hype with humility. Open data advocates argue that more transparency would solve many of these problems. If all observations were immediately released to the public, if raw data were freely available, then independent analysts, amateur astronomers, and crowdsourced efforts could contribute to the science. That's happened before with great success. Galaxy Zoo, a project where volunteers classified galaxy shapes, made discoveries that professional astronomers missed. Citizen scientists have found exoplanets, tracked asteroids, and contributed to countless research projects. But open data also has risks. Not everyone has the expertise to interpret complex datasets. Misinterpretations can spread quickly. creating confusion or false narratives. There's also the issue of credit. If a team spends years developing instruments, planning observations and analysing data, only to have someone else scoop their results by quickly analysing publicly released data, that's demoralising and unfair. The history of previous interstellar objects offers lessons. When Oumuamua was discovered in 2017, the data were relatively open, and many teams published analyses. That openness led to vigorous debate, competing interpretations, and eventually a consensus that Oumuamua was probably natural, though unusual. But it also led to fringe claims, sensational headlines, and lasting controversy, especially around Loeb's light sail hypothesis. 2I/Borisov, the second interstellar visitor, was more straightforward, behaving like a typical comet, and the scientific response was calmer, more measured. 3I-ATLAS is shaping up to be more like Oumuamua than Borisov. The anomalies are too significant to ignore, the questions too big to dismiss. And that means the politics, the debates, the battles over data and interpretation will continue. What matters most is that the observations continue, that the analysis is as rigorous as possible, and that scientists communicate honestly about what they know, what they don't know, and what the different possibilities are. If 3I-ATLAS turns out to be a broken comet, fine. We'll have learned something about interstellar objects and improved our models. If it turns out to be something stranger, then the transparency and rigour with which the discovery is handled will determine whether it's remembered as a triumph of science or a cautionary tale of missed opportunities. For now, the data is still coming in. December 19th approaches, and the world is watching. But 3I-ATLAS isn't happening in isolation. The cosmos has been delivering other surprises recently, other challenges to our assumptions, other hints that the universe is stranger and more dynamic than we realised. That's where we turn next, zooming out from this single object to the broader cosmic context. Why does this one matter? What does it tell us about astronomy, about humanity, about our place in a galaxy that keeps surprising us? That's the final piece of the puzzle, and that's where we go now. Part 10. Why this one matters. The big picture for astronomy and humanity. Step back for a moment. Take the wide view. Since humans started seriously studying the sky, since Galileo pointed a telescope upward, since Edwin Hubble showed us that the fuzzy nebulae were actually entire galaxies, we've been learning that the universe is bigger, older, and stranger than we imagined. Every generation thinks it's got the picture mostly figured out, and every generation is proven wrong by new observations. 3I-ATLAS is the latest in a long line of humbling discoveries. Only 3 interstellar objects have been confirmed entering our solar system. 3 in all of human observation. Oumuamua in 2017, cigar-shaped and tumbling, defying easy classification. Borisov in 2019, more comet-like, more comfortable, but still an outsider. And now 3I-ATLAS, the largest and most anomalous of the 3, pushing the boundaries of what we can explain. Think about the rarity. Interstellar space is vast, nearly empty. Stars are separated by light years, distances so immense that even travelling at relativistic speeds would take decades or centuries to cross them. Objects ejected from one system drift for millions of years before encountering another. The odds of detecting one passing through our relatively small patch of sky during our relatively brief observational window are low, and yet we've now seen 3. What does that tell us about the population? If we've detected 3 in less than a decade of modern surveys, how many are out there that we're missing? Estimates vary, but some models suggest there could be thousands of interstellar objects passing through the inner solar system at any given time, most too small or too faint to detect. Improved surveys, better instruments, dedicated search programs, all of these will increase the detection rate. 3I-ATLAS might be the beginning of a flood, and if interstellar objects are common, if the galaxy is constantly exchanging material between star systems, then our models of solar system formation and evolution need updating. We've thought of our system as isolated, i.e. self-contained units shaped only by internal processes, and the occasional comet or asteroid from our own Oort cloud or Kuiper belt. But if interstellar visitors are frequent, if they bring chemicals and materials from other systems, then the mixing is ongoing. The solar system isn't closed, it's part of a galactic ecosystem, exchanging matter and information over deep time. That has philosophical weight. We're not isolated. We're not alone, even if we haven't found intelligent life. The molecules in 3I-ATLAS were forged in another stellar nursery, shaped by another star's light, processed by the same cosmic forces that shaped us. There's a continuity, a connection that spans the galaxy. And if material can travel between stars, if chemistry and geology are galactic processes, then maybe life can too. Panspermia, the idea that life might spread between worlds via comets or asteroids, becomes more plausible. Maybe the building blocks of life, maybe even simple organisms, hitch rides on interstellar objects and seed new worlds. Maybe that's how life began on Earth. Maybe that's how it spreads everywhere. 3I-ATLAS also matters because of what it teaches us about planetary defence and future space exploration. If interstellar objects are common, if they can enter our system on unpredictable trajectories, then tracking them becomes a priority. Most won't threaten Earth, but eventually statistically one might. Knowing how to detect them early, how to characterise their orbits, how to assess risk, these are practical concerns that go beyond pure science. And if we're thinking about sending our own probes to other stars, missions like Breakthrough Starshot that aim to accelerate tiny spacecraft to a fraction of light speed, then understanding what those probes might encounter along the way is critical. Interstellar space isn't empty. There's dust, gas, radiation, and apparently solid objects large enough to destroy a spacecraft on impact. 3I-ATLAS gives us data on what's out there, how fast things are moving, what compositions to expect. But the real reason 3I-ATLAS matters is deeper, more existential. It forces us to confront uncertainty, to sit with the discomfort of not knowing. Is it a comet? Is it technology? Is it something we don't have words for yet? The answer matters, obviously, but the process of asking, the willingness to entertain possibilities that challenge our worldview, that's where growth happens. That's where science becomes more than data collection. It becomes a way of thinking, a way of being open to surprise, of updating beliefs in the face of evidence. If 3I-ATLAS is a broken comet, we've learned that interstellar bodies can fragment dramatically near the Sun, that carbon dioxide-dominated compositions exist in nature, that cosmic ray processing creates organic crusts on objects that wander the galaxy. That's valuable. It refines our models, gives us new data points, expands our understanding. If 3I-ATLAS is intact and doing something stranger, if there's even a small chance it's artificial, then the implications multiply exponentially. We're not alone, meaning has spread beyond Earth. Intelligence exists or has existed elsewhere, and we've just had our first confirmed brush with it. That changes everything. How we see ourselves, how we think about the future, what we prioritise as a species. It's not just an astronomical discovery, it's a civilizational turning point. And even if we never get a definitive answer, even if 3I-ATLAS fades into the distance leaving us with more questions than answers, the exercise has value. We've pushed our instruments to their limits. We've debated interpretations, refined techniques, collaborated across institutions and nations. We've engaged the public, sparked imaginations, reminded people that the universe is still full of mystery. That's worth something. That's worth a lot. The story of 3I-ATLAS is still unfolding. December 19th will bring new data. Months and years of follow-up observations will track its evolution, its trajectory, its ultimate fate. Papers will be published, debated, revised, consensus might emerge, or the controversy might deepen. But whatever happens, this object has already left its mark. It's made us think harder, look closer, question more deeply. And it's not alone in that. The universe has been serving up other surprises recently, other discoveries that challenge assumptions and expand horizons. 3I-ATLAS is part of a broader pattern, a moment in time when our observational capabilities are leaping forward and the cosmos is revealing itself in ways we didn't predict. That's where we go next, into the parallel stories, the other recent breakthroughs that complement and contextualize this strange visitor from beyond. Part 11. The universe is cooling, star formation decline. While 3I-ATLAS has been occupying headlines and telescope time, other cosmic stories have been quietly reshaping how we think about the universe's past, present and future. One of the most significant comes from the Euclid mission, a European Space Agency telescope launched in 2023 to map the large-scale structure of the universe and probe dark energy. Euclid's latest data release, which came out recently in 2025, includes findings that many people might have missed amid the comet excitement. The rate of star formation in the universe has peaked. It's now declining. The cosmos is cooling down. That might not sound dramatic at first, but think about what it means. For billions of years after the Big Bang, the universe was in a frenzy of star formation. Massive clouds of hydrogen and helium collapsed under gravity, igniting nuclear fusion, creating the first stars. Those stars lived, died, exploded as supernovae, enriching space with heavier elements. New generations of stars formed from that enriched material, creating planets, moons, and eventually the conditions for life. Star formation was the engine of cosmic evolution, the process that turned simple gas into complex structures. The rate wasn't constant. It peaked sometime around 10 billion years ago in the universe's middle age, when galaxies were colliding frequently, triggering bursts of star formation in their spiral arms and cores. Since then, the rate has been declining, slowly at first, now more noticeably. Euclid's data shows that fewer new stars are forming now than at any point in recent cosmic history. The universe is entering a quieter phase, where existing stars age and die, and fewer new ones take their place. Why is this happening? Part of it is simply that the raw materials are running out. Hydrogen gas, the fuel for star formation, is being consumed by existing stars or locked up in galaxies where conditions no longer favour collapse. Dark energy, the mysterious force accelerating the universe's expansion, is also playing a role. As space expands faster, galaxies drift apart, collisions become rarer, and the gravitational interactions that trigger star formation become less frequent. The implications are profound. Fewer new stars means fewer new planetary systems. It means the future universe will be darker, colder, more dominated by old stars and dead stellar remnants. It means opportunities for life, at least life as we know it, will become rarer. We're living in an era where star formation is still robust enough to create Earth-like worlds, but that era is finite. Billions of years from now, the universe will be a very different place, dimmer and more static. How does this connect to 3I-ATLAS? On the surface, they seem unrelated. One is a single object passing through our solar system. The other is a universal trend spanning billions of light years. But both challenge the assumption that the cosmos is in a steady state, that what we see now is what's always been and always will be. Just as 3I-ATLAS doesn't behave like a normal comet, the universe doesn't behave like a forever active star factory. Both are reminders that change is fundamental, that nothing in the cosmos is static. There's also a thematic link. If star formation is declining, if new planetary systems are becoming rarer, then interstellar objects like 3I-ATLAS might represent an increasingly important mechanism for exchanging materials between existing systems. As galaxies age and star formation slows, the objects already present, the comets and asteroids and potentially artificial probes, become the primary carriers of information and chemistry. The emphasis shifts from creation to circulation, from birth to recycling. It also shifts our perspective on detection. If interstellar visitors are becoming more common because there are fewer new stars but plenty of old systems shedding material, then we should expect more objects like 3I-ATLAS in the future, not fewer. The galaxy might be entering an era where the dominant activity is exchange rather than formation, where wandering bodies carry the legacy of dying systems to younger ones. The Euclid findings also underscore something fundamental about observation and timing. We live in a universe that's approximately 13.8 billion years old, and we're observing it at a specific moment in its evolution. That moment happens to be after peak star formation, but before the universe has gone completely dark. We're in the twilight zone, cosmically speaking, watching the engines wind down but not yet extinguished. 3I-ATLAS is passing through during this same twilight, a visitor from a galaxy where star formation peaked billions of years ago, where the objects drifting through space might be the last remnants of once vibrant planetary systems. There's a poignancy to that, if you think about it. The universe had its wild youth, its peak productivity, and now it's settling into a long decline. Not a collapse, not an ending, just a slow fade. Star formation will continue for billions of years yet, but the glory days are behind us. We're living in the aftermath of peak cosmic activity, and objects like 3I-ATLAS are the messages in bottles from that earlier era, carrying information about what came before. This connects to a broader realization that's been building in astronomy over the past few decades. The universe isn't what we thought it was. It's not static, not stable, not predictable in the ways our equation suggested. Dark energy is accelerating expansion, when we expected deceleration. Star formation is declining when we assumed it would continue indefinitely. And now, with 3I-ATLAS, even our understanding of comets and interstellar objects is being challenged. The pattern is clear. Every time we look closer, the universe surprises us. Every time we build better instruments, we find phenomena that don't fit the models. The lesson is humility. And that lesson extends beyond astronomy. If the universe at its largest scales is behaving unexpectedly, if the grand machinery of galaxies and cosmic expansion is more complex than we realized, then why should we expect smaller scales to be simple? Why should a single interstellar object behave exactly as predicted? The connection between macro and micro isn't causal, but it's philosophical. Both point to the same truth. Reality is richer, stranger, more layered than our theories capture. We're always playing catch-up, always revising, always learning that what we thought was solid ground is actually shifting beneath our feet. The Euclid findings about star formation decline are a reminder that the cosmos has a history and a future, and we're witnessing a specific chapter. 3I-ATLAS is part of that same chapter, a visitor from another part of the story, carrying clues about where the galaxy has been and where it's going. Both tell us that nothing lasts forever, that change is the only constant, and that our moment in cosmic history is precious, fleeting, and worth paying attention to. But the surprises don't stop there. If star formation is winding down, another fundamental assumption about the universe is also under fire, this time concerning expansion itself. That's the next piece of the puzzle. Part 12. Is the universe's expansion slowing? For over 20 years, cosmologists have operated under a paradigm-shifting discovery. In 1998, two independent teams studying distant supernovae found that the universe's expansion isn't just continuing, it's accelerating. Galaxies are moving apart faster now than they were in the past. This was so unexpected, so contrary to predictions, that it required inventing a new component of reality to explain it. That component is dark energy, a mysterious force permeating space, pushing everything apart with increasing strength. The discovery earned a Nobel Prize. The model became standard. Dark energy was real, acceleration was happening, and the universe's fate was a cold, lonely dispersal into infinite darkness. Except now, in 2025, a new study has thrown that consensus into question. Using updated data from multiple sources, including the Hubble Space Telescope and ground-based surveys, a team of cosmologists has suggested that the acceleration might not be real. The universe might still be expanding, but the expansion could be slowing down, or at least not accelerating as strongly as previously thought. If true, this would overturn decades of cosmology, invalidate countless models, and force a complete rethinking of what dark energy is and whether it even exists. How did this happen? How did cosmologists get it wrong for 20 years? The answer lies in the difficulty of measuring cosmic expansion accurately. The method relies on standard candles, objects whose intrinsic brightness is known. By measuring how bright they appear from Earth, you can calculate their distance. Type Ia supernovae are the classic standard candles, explosions of white dwarf stars that all reach roughly the same peak brightness. But there are complications. Supernovae aren't perfectly uniform. Dust along the line of sight can dim them, making them appear farther away than they are. The calibration of their intrinsic brightness depends on nearby supernovae, which introduces uncertainties. Small errors in any of these factors can propagate into big errors in the inferred expansion rate. The new study reanalyzed the data using improved techniques, better dust corrections, and more sophisticated statistical methods. When they crunched the numbers, the evidence for acceleration weakened. It didn't disappear entirely, but it became less certain, more ambiguous. Some models still supported acceleration, others supported deceleration, and the data couldn't definitively choose between them. The conclusion was cautious, but radical. We might not know whether the universe is accelerating or not. Dark energy, the cornerstone of modern cosmology, might be an artifact of measurement errors rather than a real physical phenomenon. This is still controversial. Many cosmologists remain convinced that acceleration is real, that the evidence is solid, and that the new study's methods introduce their own biases. The debate will continue, with more data, more observations, more analysis. But the mere fact that it's a debate, that the acceleration is no longer considered settled science, is significant. What does this have to do with 3I-ATLAS? Again, the connection is thematic rather than direct. If the large-scale behaviour of the universe, its expansion rate, its ultimate fate, can be uncertain after decades of study, then uncertainty at smaller scales shouldn't surprise us. The universe is consistently less knowable, less predictable than we'd like. Whether it's the expansion of space, the decline of star formation, or the behaviour of a single comet, the pattern is the same. Our models are approximations, useful but incomplete, always subject to revision in the face of better data. There's also a deeper connection about energy and acceleration. 3I-ATLAS shows non-gravitational acceleration, a change in its trajectory that can't be explained by gravity alone. The universe, according to the old paradigm, shows accelerating expansion driven by dark energy. Both involve mysterious forces, both challenge our understanding of how energy and motion work. If dark energy turns out to be misunderstood or non-existent, that doesn't directly affect 3I-ATLAS, but it does reinforce the idea that acceleration, whether cosmic or cometary, is a phenomenon we're still struggling to fully grasp. The philosophical implication is unsettling. We live in a universe whose basic properties, size, expansion rate, composition, future, we're not sure about. Dark energy supposedly makes up 70% of the universe's total energy content, and we don't know what it is or whether it's real. Dark matter, another 25%, is equally mysterious. That leaves just 5% of the universe composed of normal matter, the stuff we understand. And even within that 5% we find objects like 3I-ATLAS that defy easy explanation. Our ignorance is vast, our knowledge a tiny island in an ocean of unknowns. But ignorance isn't failure, it's the starting point for discovery. Every question answered reveals 10 more questions. Every mystery solved opens doors to deeper mysteries. 3I-ATLAS, the declining star formation, the uncertain expansion rate, all of these are opportunities to learn, to refine our theories, to push the boundaries of what's knowable. The universe doesn't owe us simple answers. It doesn't care whether our models work. It just is, in all its complexity and strangeness, and our job is to observe, to question, to revise, to keep looking. So the cosmos surprises us at the larger scales. What about at smaller scales, at the level of individual objects? That's where the next story comes in. Another case of weird chemistry. Another object that doesn't fit expectations. Sound familiar? Part 13, Alien Chemistry, Phosphine. Around a brown dwarf. In recent months, astronomers studying a brown dwarf known as Wolf 1130 ABC detected something unexpected in its atmosphere, phosphine. A simple molecule, one phosphorus atom bonded to 3 hydrogen atoms, but its presence in this environment was a puzzle. Phosphine is associated with biological activity on Earth. It's produced by microbes in oxygen-poor environments, swamps and marshes, and deep ocean vents. When scientists detected phosphine in the atmosphere of Venus a few years ago, it sparked a debate about whether life might exist in Venusian clouds. That claim has since been disputed, with alternative explanations suggesting geological processes or measurement errors. But the excitement around phosphine as a potential biosignature remains. Brown dwarfs are failed stars, objects too massive to be planets, but not massive enough to sustain hydrogen fusion. They glow faintly from residual heat and emit primarily in the infrared. They're ancient, often billions of years old, slowly cooling over time. Their atmospheres are complex, containing methane, ammonia, water vapour and various organic molecules. But phosphine, that was unexpected. It requires specific conditions to form and remain stable, and the chemistry of brown dwarf atmospheres doesn't obviously produce it. The discovery raises questions. Is the phosphine biological? Almost certainly not. Brown dwarfs are far too hot and hostile for life as we know it. More likely, it's the result of unusual chemical pathways, perhaps high-energy reactions driven by convection currents bringing material from the interior to the surface, or photochemical processes in the upper atmosphere. But the exact mechanism isn't clear yet. It's another case of weird chemistry, another reminder that the universe produces molecules in ways we don't fully anticipate. How does this connect to 3I-ATLAS? Both are examples of chemical anomalies, compositions that don't fit standard models. 3I-ATLAS has too much carbon dioxide, too little water, a ratio that suggests either an exotic formation environment or surface processing by cosmic rays. The brown dwarf has phosphine where it shouldn't be, a molecule that requires explanation. Both force us to expand our understanding of what's chemically possible under different conditions. There's also a parallel in how we interpret anomalies. When phosphine was detected on Venus, some scientists immediately jumped to the possibility of life. Others urged caution, pointing out that our knowledge of Venusian chemistry is incomplete, and that biological explanations should be a last resort after ruling out all natural processes. The same dynamic is playing out with 3I-ATLAS. Some see the anomalies and suggest technology. Others insist we haven't exhausted natural explanations yet. The tension between openness to radical possibilities and skepticism toward extraordinary claims is healthy, necessary, but also frustrating for everyone involved. The brown dwarf finding also emphasizes the importance of spectroscopy, of breaking light into its component wavelengths and identifying molecular signatures. That's how we detected the phosphine, how we measured 3I-ATLAS's carbon dioxide dominance, how we study exoplanet atmospheres and distant galaxies. Spectroscopy is one of astronomy's most powerful tools, allowing us to do chemistry at cosmic distances, but it's also limited by our knowledge of what different molecules look like spectroscopically, how they behave under various conditions, and what other processes might mimic their signatures. Ambiguities are common, and confirmation often requires multiple independent observations. The broader theme here is that the universe is chemically diverse, far more so than we realized a generation ago. Every new object, every new environment, reveals molecules and reactions we didn't predict. Some of that diversity comes from the range of conditions, temperatures from near absolute zero in interstellar space to millions of degrees in stellar cores. Some comes from the mixing processes, cosmic rays, supernova, stellar winds, all stirring the chemical pot. And some might come from life, from biology adding its own layer of complexity to certain environments. We don't know yet where the line is between natural and biological chemistry in the broader universe, but every discovery helps us map the landscape. 3I-ATLAS sits somewhere on that landscape, a data point we're still trying to interpret. Its high carbon dioxide could be natural, the result of formation conditions or cosmic ray processing. Or it could be something else, though what that else might be remains speculative. The brown dwarf's phosphine is almost certainly natural, a product of atmospheric chemistry we don't fully understand yet. Both are reminders that chemistry isn't simple, that molecules form and persist in surprising ways, and that our models need constant updating. As our instruments improve, as we study more objects in more detail, we'll find more anomalies, more unexpected molecules, more puzzles. That's the trajectory of science. The more we learn, the more we realize how much we don't know. 3I-ATLAS and its strange composition are part of that ongoing education, one more lesson in humility delivered by a universe that refuses to be fully known. But it's not just chemistry and composition that are surprising us. Our view of the galaxy itself, the structure and layout of our cosmic neighbourhood, is also being revolutionized. That's the next piece of the story. Part 14. Sharper Map of the Milky Way. We're seeing more than ever. For most of human history, the Milky Way was a mystery, a river of light across the night sky whose nature was unknown. Was it milk spilled by the gods, as some myths claimed? Was it a cloud of glowing vapour? It wasn't until the 1700s that we realised it was made of countless individual stars, and not until the 1920s that we understood our sun was just one star among hundreds of billions, all orbiting in a vast spiral disk. But even with that understanding, mapping the Milky Way remained incredibly difficult. We're inside it, embedded in the disk, surrounded by dust and gas that obscures our view. It's like trying to map a forest while standing in the middle of it with fog all around. In recent years, that's changing. Missions like Gaia, the European Space Agency telescope launched in 2013, have been measuring the positions and motions of over 1 billion stars with unprecedented precision. By tracking how stars move, astronomers can reconstruct the Milky Way's structure, identifying spiral arms, stellar streams and hidden features. Radio telescopes have added another layer, mapping hydrogen gas and tracing the galaxy's magnetic fields. Infrared surveys pierce through dust clouds to see star-forming regions previously invisible. The result is a sharper, more detailed map of our galaxy than ever before. The latest data, released in 2025, reveals structures that weren't known or understood before. New spiral arms, streams of stars torn from disrupted dwarf galaxies, clumps of dark matter inferred from gravitational effects, all appearing in the data like ghosts materializing from fog. The Milky Way is more complex than the simple four-armed spiral we used to teach in classrooms. It's lumpy, asymmetric, filled with substructures and streams and regions where star formation is happening or has recently ended. One particularly interesting feature is a recently identified stellar stream, a river of stars moving together through space, likely the remnant of a small galaxy that the Milky Way consumed millions of years ago. These streams are fossils of past collisions, evidence that our galaxy hasn't grown in isolation, but has been cannibalizing neighbours throughout its history. Some of those neighbours might have had their own planetary systems, their own comets and asteroids, which are now mixed into our own. 3I-ATLAS could be a descendant of such a system, ejected during a galactic collision, wandering for eons before passing through our neighbourhood. The improved mapping also reveals the distribution of objects in interstellar space. By tracking velocities and densities, astronomers can estimate how much material is drifting between stars, how often collisions or close encounters happen, and what the population of rogue planets, comets, and asteroids might be. The numbers suggest that interstellar space isn't as empty as we once thought. There's a lot of stuff out there, most of it dark and invisible, but occasionally something like 3I-ATLAS comes close enough and bright enough to detect. This connects to the earlier point about the declining star formation rate. If the Milky Way is aging, if fewer new stars are being born, then the material in the galaxy isn't being concentrated into new systems as quickly. Instead, it's spreading out, forming a diffuse population of wanderers. Those wanderers, over time, become the interstellar objects that might visit other systems. The better we map the galaxy, the better we understand that population, and the better we can predict how often objects like 3I-ATLAS should appear. There's also a practical angle. As humanity considers interstellar exploration, as projects like Breakthrough Starshot plan to send tiny probes to nearby star systems at relativistic speeds, understanding what's between here and there becomes critical. A collision with even a small grain at 20% of light speed would be catastrophic. Mapping the dust, gas and larger objects along potential routes is essential for mission planning. 3I-ATLAS gives us a data point, a sample of what's out there, what compositions to expect, what hazards to plan for. The sharper map of the Milky Way is also aesthetically and emotionally significant. It's our home galaxy, the cosmic structure we're part of, and seeing it more clearly is like getting a better view of your own house after living there your whole life. The spiral arms, the stellar streams, the regions where new stars are forming, all of it becomes more real, more tangible. We're not just abstract observers, we're participants in the galaxy's ongoing story, shaped by its history, influenced by its dynamics, connected to everything else through gravity and chemistry, and the exchange of materials. 3I-ATLAS, in that context, isn't just a visitor, it's a messenger, carrying information about another part of the galaxy, linking our system to the broader structure. When we study it, we're learning not just about one object, but about the processes that shape the entire Milky Way. Every interstellar visitor is a piece of the puzzle, a sample from the vast laboratory of galactic evolution. And as our maps improve, as our instruments become more sensitive, we'll detect more visitors, build up statistics, start to see patterns. Maybe we'll find that certain types of objects come from certain directions, suggesting specific source regions. Maybe we'll detect streams of interstellar material, rivers of comets and dust flowing through the galaxy. Maybe we'll find something that doesn't fit at all, something that forces us to reconsider what's possible. That's the trajectory we're on. A path toward greater understanding, but also toward greater mystery, because every answer reveals new questions. The final piece of this broader cosmic context brings us back to Earth, to humanity's own future in space. While we study visitors from other systems, we're also preparing to become visitors ourselves, to send probes and eventually people beyond our own neighbourhood. That's where the story comes full circle. Part 15. From Visitor to Voyager, Human Spacefaring Futures. While 3I-ATLAS has been reminding us that interstellar objects are real, are detectable, and are deeply strange, humanity has been quietly preparing for its own role in the interstellar story. We're on the cusp of becoming not just observers of cosmic visitors, but voyagers ourselves, sending probes beyond the solar system, establishing infrastructure on the Moon and Mars, and developing the technologies that might one day allow us to reach other stars. The past year has seen significant advances in space robotics and in situ resource utilization, the practice of using materials found in space rather than launching everything from Earth. NASA's Artemis program, aimed at returning humans to the Moon, has been testing robotic systems that can extract water ice from lunar craters, split it into hydrogen and oxygen for fuel, and 3D print structures from lunar regolith. Private companies are developing mining techniques for asteroids, targeting metals and volatiles that could be worth trillions of dollars. The vision is to establish a space-based economy, where raw materials are harvested in space, processed in space, and used to build spacecraft, habitats and infrastructure without the enormous cost of escaping Earth's gravity well. These developments matter for interstellar exploration. If we're going to send probes to other star systems, and if those probes are going to be anything more than tiny chips accelerated by lasers, then we need to build them in space using space resources. We need manufacturing facilities in orbit or on the Moon. We need fuel depots, repair stations, launch platforms. The infrastructure we're building now for lunar and asteroid missions is the foundation for future interstellar capabilities. There are also advances in propulsion. Ion drives, solar sails, nuclear thermal rockets, all are being tested or considered for deep space missions. None of them can reach relativistic speeds yet, but they're steps in that direction. Understanding how different propulsion systems behave, how exhaust plumes look, how trajectories are altered, all of this feeds back into our ability to interpret observations of objects like 3I-ATLAS. If we suspect it might have propulsion, knowing what propulsion looks like from our own technology helps us recognize anomalies. The connection runs both ways. Studying 3I-ATLAS teaches us about the interstellar environment, about what our probes might encounter, about the composition and hazards of objects drifting between stars. If we're going to send something to Alpha Centauri or another nearby system, it needs to survive impacts with dust, handle radiation, potentially navigate around larger debris. Every interstellar object we study is reconnaissance, gathering intelligence about the conditions out there. There's also the possibility, however remote, that 3I-ATLAS is itself a probe, that we're studying someone else's engineering. If true, then it's a benchmark, a comparison point for our own efforts. How do they build things? What materials do they use? How do they power their systems? Even if we can never definitively prove it's artificial, the speculation pushes us to think about what interstellar probes should look like, what features they need, what trade-offs are involved. It's engineering by analogy, learning from a hypothetical example. But beyond the technology, there's a deeper question about why we're doing this, why we're investing in space exploration when there are pressing problems on Earth. The answer, at least in part, is that studying objects like 3I-ATLAS reminds us that Earth is part of something larger. We're not isolated. We're in a galaxy full of stars and planets and objects that move between them. Understanding that context, participating in that exchange, is part of what it means to be a spacefaring civilization. It's not just about resources or scientific knowledge, though those matter. It's about perspective, about seeing ourselves as one thread in a vast cosmic tapestry. 3I-ATLAS, whether it's a comet or a probe or something in between, is a reminder that the universe is active, dynamic, full of motion and change. Objects travel between stars. Material spreads through the galaxy. And if material can spread, if chemistry and perhaps even life can hitch rides on comets and asteroids, then so can we. The visitors we see today might be previews of our own future, a future where human-made probes drift through other star systems, carrying information about Earth, about our chemistry, our culture, our existence. That future is still speculative, still decades or centuries away. But the groundwork is being laid now, in lunar missions, asteroid surveys, propulsion tests, and observational campaigns targeting interstellar objects. We started by asking what happens if 3I-ATLAS broke apart near the Sun, what it means for us. The answer is complex. Scientifically, it depends on whether fragmentation occurred, what the composition is, whether natural processes can explain the anomalies. Philosophically, it depends on how we interpret the mystery, whether we see it as a random comet or a message, a threat or an opportunity. But the broader answer, the one that encompasses all the parallel stories we've explored, is that 3I-ATLAS is part of humanity's ongoing education about the cosmos. It's teaching us that the universe doesn't behave the way we expect, that models need constant revision, that every discovery opens new questions. It's showing us that interstellar space isn't empty, that exchange between star systems is real, that we're part of a galactic ecosystem whether we realise it or not, and it's reminding us that our moment in cosmic history is special, that we live in an era where we can detect these visitors, study them, learn from them, and perhaps one day join them. The universe is cooling down, star formation is declining, the expansion might be slowing or accelerating or doing something we don't understand yet. Chemistry is weirder than we thought, objects don't fit our categories, and the galaxy is more complex than our maps showed. In the middle of all that uncertainty, 3I-ATLAS appeared, bright and strange and impossible to ignore. It disrupted our assumptions, sparked debates, captured imaginations. What happens to us if it broke apart? We gain knowledge, refine our models, prepare for future visitors. What happens to us if it didn't? We face bigger questions, stranger possibilities, a universe that might be more populated, more alive, more connected than we dared to imagine. Either way, we're changed by the encounter. We've seen something that challenges us, that pushes us to think differently, to look harder, to question more deeply. And maybe that's the real answer to the original question. What happens to us isn't about physical danger or asteroid impacts or debris fields. It's about perspective. It's about being reminded that we live in a vast, ancient, mysterious universe that we're only beginning to understand. 3I-ATLAS, whatever it is a gift, an opportunity to learn, to grow, to see ourselves and our world in a larger context. The observations will continue. December 19th will bring better images, more data, clearer answers or deeper mysteries. Scientists will debate, papers will be published, consensus might emerge or the controversy might deepen. But regardless of how the technical questions resolve, the experience of studying 3I-ATLAS has already changed us. It's made us more aware of the possibilities, more open to surprise, more humble in the face of cosmic complexity. We are the species that looks up, that asks questions, that builds telescopes and sends probes and wonders about our place in the universe. 3I-ATLAS is part of that story, a visitor from beyond that reminds us the journey is far from over. The cosmos is stranger than we thought, and we're in the middle of learning just how strange. That's not a conclusion, it's a beginning.